So Unit 4, Lesson 1, this is kind of the culminating lesson before we jump to Riemann Sums, which is going to be jumping back and forth between different notations. And that's generalizing to more and more rectangles. I guess I only typed more once. But so eventually you need to be able to represent sums in sigma or summation notation. I made a separate video about that. So today I want to show you how we're going to generalize rectangular approximation techniques to create formulas for any number of rectangles. So you should be able to create left, right, midpoint rectangles and, draw them out, find the area, add them together for, let's say, 2, 3, 4, 5 rectangles. But today, well, eventually, if you're in my class, you already know this, we're getting to infinitely many rectangles. We're going to put limits on things. Everything in calculus AB involves limits. Except maybe average rate of change, but that's neither here nor there. So today we're going to go to 5, 10, 100, 1,000 rectangles. And I want you to know where those formulas come from. If you know where they come from, I think it's a little bit easier, or it's actually incredibly straightforward. So just watch out in my class. Make sure you're addressing the task. If you're asked for an approximation itself, you need a numerical value, which I'm going to ask you for here eventually. Everything should add up, ignoring addition, subtraction, multiplication, division. You can't leave the F's in there. But either way, you need to show where the values come from. So you can't just start writing numbers. Anyway, so let's do a quick checkup. Make sure you're on board. Make sure you're ready for this. If you have no idea how to do this, or this is a struggle, I think we need to go back and practice more before generalizing to more rectangles. So g of x is a parabola x squared plus 1 on the interval -1 to 3. And we're going to write some expressions. One to approximate the area under g on -1 to 3 using 4 left-hand rectangles. Another approximation using 4 right-hand rectangles, and one using 4 midpoint rectangles. So I've used Desmos to create a handy-dandy chart here. I made everything easy. Total width of 3 minus -1 or 4 gives us 4 wide divided into 4 equal-sized pieces, which means, well, everything should be pretty straightforward. So give ourselves a label, the area under g of x, which is x squared on -1 to 3 using 4 left rectangles. So what's that first area, that pink area? Well, that's a width of 1, but because we're given a graph, or I gave it to you, a better way to write that would be 0 minus -1. And we're finding the height at the left-hand endpoint -1, so we'll multiply by g of -1. Let's go back. It says write an expression to approximate the area. I don't really feel like approximating. It didn't say approximate the area. It said write an expression that could be used to approximate. Okay, so what are we going to write for the width of that green rectangle? Well, 1 minus 0, and we're finding the height at the left endpoint, 0, so 1 minus 0 times g of 0. What about this orangey rectangle? That's a width of 2 minus 1 times a height g of 1. And that last purple rectangle, that's a width of 3 minus 2 times a height g of 2. All right. So now let's find the area under g of x, same thing on -1 to 3 using 4 right rectangles. And, most of this is going to be the same, 0 minus -1, but instead of g of -1, we're doing height on the right-hand side, so g of 0. 1 times 0 for the width, and what are we going to use for the height? G of 1. 2 minus 1 for the width, g of 2, 3 minus 2 for the width, and g of 3 for the height. So if you're thinking this is straightforward, cool. You are ready for what I'm about to bring. Now, we're actually not going to use midpoint rectangles today. In fact, we're not going to use left-hand rectangles, but you still need to know how to do this. And we have everything set up. So I'm just going to give you the structure. Same widths. In fact, I didn't even rewrite them. I cut and pasted them. What are we going to put in for these inputs? 0 minus -1, g of -1/2. 1 minus 0 times g of 1/2. 2 minus 1 times g of 3/2, and 3 minus 2 times g of 5/2. Okay, hopefully we're good to go. So the first thing we're going to do, we're just going to keep using 1 over x because the function doesn't really matter. And 1 over x is discontinuous, but we're only worried about what's going on in between 1 and 2. So we're going to approximate this area using 5, 10, 100, 1,000 different rectangles, which sounds daunting. But if we know where the numbers come from, then these are actually all the same level of difficulty, which might seem a little bit crazy. And so I think the easiest thing is to use right-hand rectangles, because then the height of the first rectangle is 1 width away from the left-hand endpoint. And that's true. You know, I've drawn in, whatever, Desmos has drawn in 5 rectangles, but if there were 5 rectangles or 100 or 1,000 rectangles, doesn't really matter. The first place that we're going to be finding the height is 1 width away from the left-hand endpoint. And, you know, it's just the widths that are going to change. You know, maybe the width is 1/5, or maybe the width is 1/10, or maybe the width is 1/100th. It doesn't really matter how many widths there are. And the second width, or the second x coordinate, where we're going to find the height for the second right-hand rectangle, you know, is going to be 2 widths away from the left-hand endpoint. And again, that doesn't matter if we're doing 5 rectangles like this, or 10, or 100, or 1,000. Okay, so I have this little guy right down here. We're going to approximate the area under 1 over x on the interval 1 to 2 using 5 right-hand rectangles. The first thing we need to do is figure out how wide each of those rectangles are. Nope, we're doing that later. Totally forgot. So each of those rectangles is 1/5 wide. Why 1/5? Well, how far is it from 1 to 2? 1 wide divided into 5 equal-sized pieces is 1/5. Okay. And then, you know, the next thing, what function are we putting in inputs into? Well, 1 over x. Okay, so turns out the first input is 1 over 1 plus 1/5. So, I wish I had a third color. Gosh darn it. Oh well. Let me get white. White's my favorite to draw in this color. Okay, so I've given this one a different color. That's the left endpoint 1. And maybe I should put some parentheses in here. That 1 plus 1/5 in the denominator, well, let's just ignore that, right? That's 1 over x, and this is going to be 1 over something, 1 over something, 1 over something, 1 over something. Okay, so like I was trying to tell you before, where are we finding the first height? We are finding it 1 width, 1/1/5 away from the left-hand endpoint, right? Which is, of course, you know, 1 and 1/5. So in the next input, I still have 1 over, because I'm using my function 1 over x, and I still have the left-hand endpoint. But what is this 2/1/5? Well, if you look down in the right-hand corner, if I can get the right color for me, right, where are we finding the height? Well, we are finding the height 2 widths, 2/1/5 away from the left endpoint 1. Okay, the next input is 1 plus 3/1/5. And again, hopefully that makes sense. You know, we found the first height 1/1/5 away from the left endpoint 1. We found the second height 2/1/5 away from the left-hand endpoint 1. And this is going to be, we're finding the height 3/1/5, 3 widths away from that left-hand endpoint 1. Okay, and I'm sure you see the pattern. So I know if you know, you're in a calculus class, you get that the next number is going to be 4. But why is that? Well, if we're using 4 right-hand rectangles, we're finding the height at 1 plus 1/5, you know, plus 1/5, plus 1/5, plus 1/5, 1/5, that doesn't look like 1/5, maybe they all don't. You know, it'd be 4/1/5 to the right of x equals 1. And of course that last one is 5/1/5 away from that right-hand endpoint, or left-hand endpoint, x equals 1. Okay, so we probably don't want to write things out a whole bunch of times if we're going to be using 10, 100, 1,000 rectangles. So hopefully you noticed, you know, that that width of 1/5 is repeated over and over and over again. We might as well write that width out front. So we'll just write 1 over 5 out front. And then I guess we will just recopy each of those. 1 over 1 plus 1/5, 1 over 1 plus 2/5, 1 over 1 plus 3/5, and so on down the line. Now, reading the instructions, and this is the last one we're going to do because I'm just worried about how to make these. We're going to approximate the area under 1 over x. So we actually need a y value. Now this kind of counts because we haven't, there's nothing to do but addition, multiplication, and division. But we probably want something a little bit cleaner, you know, if we have to multiple choice, choose something that matches or whatever. So what I see is, you know, this is 1/5, 2/5, 3/5, 4/5, 5/5. So I'd probably rewrite this as, you know, 5 over 6, because, you know, this denominator, that's going to be 6 over 5. And so we just write the reciprocal of that, 5 over 6. Likewise right here, that denominator is 2/5 plus 5/5 is 7/5. So let's just rewrite that reciprocal. I think that looks pretty and easy to go. Okay, so that was round 1. If you knew what I was going to write, we're ready for round 2. So this time we're going to write, but do not evaluate an expression that would give the approximation of the area. So this is nice. I just have to write things out. I don't have to simplify or anything like that. Using 10 right rectangles. Now, if you know sigma notation, you have to go back and forth. So we're going to do this kind of the long way. Okay, so we are not going to do that. So the first thing to calculate is the width. And I'm still thinking of this figure. I'm just, instead of counting 5 rectangles, I'm imagining they're 10. So what's the entire width? Well, that entire width is 2 minus 1 divided into 10 equal pieces. Each rectangle is going to be 1/5 wide. And that means we're finding the height of the first rectangle. We're still doing 1 over, because we're still using that function, 1 over x. We're finding the height of the first rectangle, you know, 1 width away from the left-hand endpoint. Oh, shoot. And we're finding the height of the second rectangle 2 widths away from the left-hand endpoint. Gosh darn it. Right? And it really doesn't matter that my picture has 5 rectangles. You can just kind of pretend, you know, and then that third height is going to be determined 3 widths away from that left-hand endpoint 1. Remember this, gosh darn it, I need to have the same color drawing on light and dark. Oh, maybe green, I can do that. There we go. You know, this one, this one, this one, that all refers to this x equals 1 left-hand endpoint. That's why that's there. Okay. Well, what goes in each of those? Of course, it's a 1/10, which, you know, matches this guy out front. That's 1/10 wide. So down below, I would add 1/10 to the left endpoint 1 to find the x coordinate to find the first height. And so 1 over 1 plus 2 versions of 1/10, 1 over 1 plus 3 versions of 1/10. Thinking ahead, we're not going to write out 100 different terms to make a sum. So, you know, 1, 2, skip a few. We need to write out the first 3 terms to establish our pattern, and I think that's pretty obvious, you know. Even if you didn't understand what this means, most reasonable people would be like, I'm pretty sure I know what the next one is, 1 plus 4 over 1/10, you know, especially since we've highlighted the colors. So we've established a pattern. We need to say where that pattern ends. And that pattern is going to end with 1 over 1 plus some number of tenths and 1 over 1 plus some number of tenths. Well, you know, the first rectangle had a 1 1/10. The second rectangle had a 2 1/10. The third rectangle had a 3 1/10. The 10th rectangle will have a 10 1/10. In fact, I think I have that animated. I do. And then the penultimate, the second to last rectangle, is going to have 1 less than 10, 9 1/10. So notice, just kind of pretending, you know, we can get pretty good here. That shouldn't feel like much different than when we were doing 5 rectangles. If you agree, cool, because we got to go way back. 5 rectangles, kind of the same idea. And so now, well, is it going to be much more difficult doing 100 right rectangles? Well, let's look back at our picture. Not really. Because the first rectangle is going to have its height determined 1 plus 1 width away from the left-hand endpoint. Or 1 is the left-hand endpoint, 1 width away from the left-hand endpoint. And you know, the next one is going to be 1 plus 2 widths Or at least that's what's going to be inside our 1 over x. Okay, cool. So what should we do? First, we want to get the width of each rectangle, and that's going to be the right-hand endpoint 2 minus the left-hand endpoint 1 divided into 100 equal-sized pieces. Do you know what the first y value is going to be? Because remember, we are doing rectangles, width times height. Well, we kind of already know, right? It's going to be 1 over, it's 1 over x, so it's always 1 over, 1 over, 1 over. And then again, it's left endpoint 1 in every single one. That's the easiest way to reference. And then this is 1 width, 2 widths, 3 widths, all the way down the line. And of course, each of those widths matches this width out front. So that's 1 over 1 plus 1 100th, 1 over 1 plus 2 times 100th, 1 over 1 plus 3 times 100th. Of course, the last two are hundredths as well. Can you figure out what our multiplier is going to be? Well, again, we have 100 rectangles. The first rectangle, we used a multiplier of 1. The second rectangle, we used a multiplier of 2. Third rectangle, a multiplier of 3. So the 100th rectangle, a multiplier of 100. And the 99th rectangle, a multiplier of 99. Okay, cool. Now we're rocking and rolling. If this is making sense, and I think it is, doing 1,000 right rectangles is trivial. Give me 1,000,000. Don't give me a number like 578 because I don't really want to write 578. We're going to start off pretty easily. The width of each rectangle is 2 minus 1 over 1,000. And then what are we going to multiply by? Well, we know it's going to be 1 over, still left-hand endpoint 1, plus 1 width, plus 2 widths, plus 3 widths, plus whatever widths. What are each of those widths? 1,000. 1/1000th. Gosh darn it. Anyways, so, I already had them filled in, 1, 2, 3, for each of those first 3 widths, because the first width is, every time, 1 width. Or the first x coordinate to find the height is 1 width away from that left endpoint 1. Okay. So, and this should be getting easier too. 1,000 right rectangles. The last term has 1,000 multiplier. And, oh, you know what we probably should have said by now? What's 1 plus 1,000 times 1 over 1,000? Well, that's 1 over 2, meaning 2 is the input, and that's this 2 here, right? Because we're putting 2 into 1 over x. Notice if we go back to the previous one, we actually have 2 as well as the last input. 100 times 1 over 100 is 1, plus 1 is, this exact same 2, which makes sense if we're doing right-hand rectangles. Notice that was actually true all along. 1 plus 10 times 1 over 10. Oh, again, we get 2 as the input. Okay, that's kind of cool. Probably should have mentioned that earlier. Okay. All right, now we get to the nitty-gritty. So we're going to write, still not evaluate an expression. We're still using 1 over x. We're still doing 1 to 2, but now we're using an unspecified number of rectangles, right? The only way we're going to do a limit, and that's what we're doing eventually, as the number of rectangles approaches infinity, which will lead us to area under a curve, which is, weirdly, if you use infinitely many rectangles, you get exact area even under something curvy. Imagine a stack of papers or something like that at the edge of it. Anyways, we need to have unspecified number of rectangles, but all we have to do is the exact same thing we did with 1,000 rectangles. So that would just be, well, my width is going to be 2 minus 1 divided into n size pieces. Well, what about the others? Well, again, notice that was kind of the same. The first rectangle is going to have its height determined. Well, this 1 was always the same because it's always the left-hand endpoint, x equals 1, the endpoint of the interval. Plus 1 width, 1 plus 2 widths, 1 plus 3 widths, and so on. So we're actually going to have that here. And notice what's the width? 1 over n. So 1 plus 1 width, or 1 plus 1, 1 over n. All right, so what's the next term? Well, of course, 1 over, because it's 1 over x, but 1 plus 2 versions of that width, 1 over n. And then 1 plus 3 widths as the input. So 1 over 1 plus 3 times 1 over n. Now we're going to skip a few. I think it's easiest to write the last one. And then we'll just, do the one right before that. But we made this, we went into a pattern and it was pretty easy. When it was 1,000 right rectangles, this last multiplier was 1,000. And again, we got that 1,000 times 1 over 1,000 is going to give us 1, and the last input is 2. Okay. So here, when it was 100 right rectangles, that last input was 100. And we got, 1 plus 1, we got an input of 2. So we can use both of those to help us out. And what's that last one? Well, of course, it's an n. We're using n rectangles. That matches up. And you can see, again, those n's could, if you want to, imagine multiplying those out to get 1, and you get 1 plus 1, and that last input is 2. Well, what's the previous term then? Well, it's 1 less than whatever the number of rectangles is. So we'll just write n minus 1. Okay. There we go. We're making progress here. But that's not as generalized as we need to be because, maybe we're not always using that same interval 1 to 2. Have we done enough pattern building where A and B, the left-hand endpoint of the interval, the right-hand endpoint of the interval don't matter? Gosh, I hope so. Well, how are we finding, the first thing we need to do is figure out this thing out front. And it doesn't really matter what A and B are. If it was 5 and 7, what would that width be? It'd be 2. If it was 5 and 17, that'd be a width of 12. Every single time, all you're going to do is right endpoint minus left endpoint divided by number of rectangles. And so why is the first term 1 over a plus 1 times b over a minus n? Well, because we were always doing the same thing. Here's 1 over x. And the left endpoint is a, and we find the first rectangle's height, one width, which is a b minus a over n. But in general, it's just one width away from the left-hand endpoint. Where are we going to find the next width? Well, or the next height is 2 widths away from that left-hand endpoint. So the next term is 1 over a plus 2 times b minus a over n. And again, that denominator is just left endpoint plus 2 widths. Okay, so what's the next one? 1 over a plus 3 times b minus a over n, right? 3 widths away from the left-hand endpoint. And of course, the next one would be 4, so we'll skip all of those. And then, what's the last term? Well, we know it's 1 over. In fact, we know it's 1 over a plus. And it's how many widths away? Well, it's n, and we did that last time. Now, let's pull that out. A plus n times b minus a over n. We should get b as the last input. So notice the n's divide, and you have a plus b minus a. No, that's definitely b as the last endpoint. All right, there's only one more thing to generalize. So notice we didn't specify number of rectangles in this one. We didn't specify the interval. And now let's just not specify what function. Again, if you understand what these things mean, this is normally, I think, where most people start in a calculus textbook. Just copy down, and, we're good to go. I think this is a better way to go if you understand where this stuff comes from. Pretty straightforward. What's the width of each interval? B minus a over n. That's unaffected by changing the function. So maybe we can think of, some function. If we're using right rectangles, where are we finding the first height? We're finding the first height 1 width away from the left-hand endpoint. So that's going to be f of a plus b minus a over n. In fact, they're all going to be f of a plus b minus a over n's, right? Because we're always measuring away from that left-hand endpoint. And the first input is going to be 1 away from the left endpoint, 2 away from the left endpoint for the second input, 3 widths away from the left endpoint for the third. And then, well, we've already done the thinking. N rectangles away, n widths away from the left-hand endpoint, and hopefully you can see, You know, the n's divide out. A minus a is 0. So that last input, again, is the b. And of course, the penultimate term has an n minus 1 there. Okay, that's actually all we need. If you got that, you are going to be good to go.